Hi, I'm Mark Weitzman, and welcome back to my video series on symmetry and group theory in physics. And today I want to start a new lesson on group representations. And this is the key to the applications in physics and everything. So let's start by defining what group representations are. So let's say we have a group G. Let's say it's finite for now. When we get infinite groups, we also have representations, but they're a little bit harder to handle. So we want to handle just a finite group G. Let's say it has order n. So it has n elements. And the idea of a representation is to simply associate a linear operator with each group element. Now, since we're dealing with finite groups and finite representations, not only is the group finite here, but I'm going to use operators that are finite dimensional to represent them. So they're also infinite dimensional, like matrices that represent them, but we're just dealing with finite. So for each element of the group, we're going to associate a matrix, and we have to have two things that are satisfied. Let's call D. I'll usually use the symbol D for the representation. By the way, since we're having linear operators on a finite dimensional space, we can always use matrices. So when I say a representation, I mean a matrix representation. We're just going to have finite dimensional matrices for each group element, and they're going to all have the same dimension. But the dimension doesn't have to have anything to do with the number of elements in the group. So we could have a one-dimensional representation of a large group. That means we associate a single number with each group element. Or we could have a two-dimensional representation of a large group. We associate a large finite group. We associate two-dimensional matrices with each element. And what we have to have is the following two things. First of all, we're going to associate with the identity element in the group, we're going to associate the identity element. And let's say the dimension of the representation is I. So we're going to do I by I matrices. So, you know what? I don't like that letter I. Let's use P. So that means we're going to associate the identity matrix in P dimensions with the identity element. And the other thing that we have to have is we have to have D of G1, G2 equals D of G1 times D of G2. These are all P, P, and P. Some books put the P upstairs, some books put the P downstairs. For the most part, don't worry about whether I put an index upstairs or downstairs. It really won't matter for a long time. So this basically says that, you know, the matrices represent the groups in the sense that if you take a product of elements in the groups, this should be for all G1, G2, and G. If you take a product of elements in the groups like G1, G2, let's say that equals G3, another group element, then the matrix representing G3 is just the product of the matrices representing G1 and G2. So the idea here is to do multiplication. We're getting the same, we can multiply the matrices, which we're comfortable with and we're used to, instead of multiplying group elements. The other thing is this is p-dimensional. So we're going to use p-dimensional matrices to represent the group elements. Now, these matrices, the representation which maps a group element G to D of G, doesn't have to be one-to-one or onto or anything. If it's one-to-one, we say it's a faithful representation. But for finite groups, we're never going to map to the whole vector space. There are definitely going to be other matrices, let's say in this p-dimensional space, there's going to be other matrices where group elements don't map to. So, because there's always an infinite number of matrices in a p-dimensional space. So one-to-one means it's a faithful rep, and if not, it's considered an unfaithful representation. But that's okay, and we'll have that a lot of times. So let me start giving you some simple examples. For instance, the easiest representation, trivial representation, for every group simply says that the element G maps to 1. Okay? So we just associate this is a one-dimensional representation. And we simply map every group element to number 1. And clearly, since every group element, the identity element in one dimension is just the number 1, so this is satisfied. And then 1 times 1 is 1. So this is a trivial representation. And it's definitely not a faithful representation. This is an important representation because, first of all, for a lot of our theorems and everything, we're going to have to count representations and everything. And this counts as one representation, so we can't leave it out. Also, sometimes this representation sort of leads to the symmetric representation. So I'm going to go back to our, I left off last time. I want to review this real quickly. We had our group S3 where we had an equilateral triangle. And we had 6 permutations of this group S3. Permutation group on 3 objects. And so we had 3 elements. We had 6 elements. There's 3 factorial group elements. And the symmetries of this triangle are reflections about the perpendicular bisectors and rotations, 2 rotations. So let me just write them again. So we have E, which is the identity permutation. We have, we can reflect about the 1 axis. I'll just put identity for the identity permutation. We reflect about this axis, and that just flips 2, 3, so that's represented by this transposition. We have R2 flips about the 2 axis, so that flips 1, 3. And we have R3 that flips about this axis, so that's 1, 2. And then we have the rotation, two pi over 3, which we rotate by 120 degrees, so 1 goes to 2, goes to 3. This is a 3 cycle. And then we have the rotation 4 pi over 3, which is the 3 goes to 2, goes to 1, reverse permutation. So these are our 6 group elements. Now, our first trivial representation we just everything goes to 1. We just assign the number 1 to this representation. Now there's another one, so this is trivial representation, so I'll call this 1. And there's also, I'll call this 1s. And then there's also 1, I'll call this, you know what? Sorry. I'm going to call this, this is the, well, I'm going to just call it 1 prime for now. This representation is also one-dimensional, and you can check it out. And if you remember, we have even permutation. This is a transposition, so it's 1 transposition, so this is an odd permutation and odd permutation. These are all in 1 class. This is in a class. This has 0 transpositions. This has 1 transpositions. And if you remember, we can write this as 1, 2, 2, 3. We can write this as 3, 2, 2, 1. So this has 2 transpositions. So these over here are what's called even permutations, and these are called odd permutations. So now we can have another representation where even permutations are given the number 1, and odd permutations are given the number -1. So this is like a parity representation. We can split our symmetries into 2 groups, those which have even parity and those which have odd parity. So this is a one-dimensional representation. Now, there's a 2-dimensional representation. Here, what we're going to do is we're going to assign to each group element a 2-dimensional matrix. And where these come from, I'll explain in a while, but for now I'm just going to write them down. So I'm going to write down D. I'll put 2 because it's the 2-dimensional representations. So the identity element always maps to the identity matrix. I'm doing these group elements a little bit out of order, but there's a reason for that. Now, for those of you, in physics, you guys remember that a rotation, in general, r of theta, we can represent it on the coordinates, like here, x is this way, and y is this way. So, those of you remember, the easy way to do rotation is a cosine theta, and then the only other question is which one gets the minus sign here. I think I'm going to do this as minus sine theta and sine theta. I don't want to fight about which one gets the minus sign. There's active and passive rotations, and they're reversed in either one, but this will be a representation. So here for 120 degrees, you can see we get cosine 120 is minus 1/2. Sine 120 is the square root of 3 over 2. We take the minus, we got minus the square root of 3 over 2. Square root of 3 over 2 minus 1/2. So that's where the representation for the rotation matrix is. We're just rotating coordinates, x and y. Let me do d2 r 4 pi over 3 and minus 1/2 square root of 3 over 2 minus the square root of 3 over 2 and minus 1/2. So 240. Let me see, cosine is 90, yeah, it will be negative. So this is just substituting 240 degrees or 4 pi over 3 in the in that general formula for the rotations. Now we got 3 other group elements, the reflections. So here too, if you look at this, let's start with the simple one, R3. If we flip this one into this one, forgetting about where it ends up, it's obvious that, you know, from our first lesson, for instance, if we had a little displacement this way, it would end up over here when we flip through here, and x1 would go to minus x1, and y stays the same. So this is the obvious one. When we flip through R2, it's a little harder to calculate exactly how these things work, but you can verify that this represents how the displacement vectors flip when we do reflections. So this is a 2-dimensional representation of the symmetric group S3. And the important thing is, this is an irreducible representation. These two over here were also irreducible representations, but 1-dimensional representations are always trivially irreducible. So, what do I mean by irreducible? When I represent, let's say I have a big matrix for the group elements like this. A lot of times you can put them for all the group elements, not just for one group element. It's pretty easy to diagonalize one matrix, but it's hard to diagonalize all these matrices. And for this 2-dimensional representation, you can't simultaneously diagonalize all these representations, all these matrices, because they don't commute. And you can't diagonalize operators that don't commute. But sometimes when you have, like, let's say you have a 3-dimensional representation, you might be able to get it like this. And what this means is, and this is like a 2 by 2. And this 0 is like 0, 0. And this 0 is like 0, 0. So you might be able to put all the matrices in the form where it's what we call block diagonal. If you can do that, the representation is reducible. And what we're trying to do with the symmetry and the group theory, first thing we want to do when we have a group is find all the irreducible representations. And for this particular group, S3, we found them. There's one two-dimensional representation and two one-dimensional representations. Those are all the irreducible representations for S3. But there are a lot more representations for S3, higher dimensional ones and everything. So sometimes in our physics problems, what we do is we look at the problem we're getting in a higher dimension, we find the representation, and then we use the theorems that we're going to talk about in the next couple of lessons to break up that reducible representation into irreducible representations. These are like the building blocks. You know, this is a building blocks. These two don't really interact. This is called a direct sum representation. It's the direct sum of this representation and this representation. But I emphasize once again, you have to do this for every group element in the group, not just for one group element. You know, E is diagonal here, R3 is diagonal here, but these aren't diagonal. So I just want to go on to illustrate this. I want to give another representation. For every permutation group, I can give what's called a defining representation. Basically, I think of as having n objects. So these are the integers, or the objects. And then I assign to each permutation P, let's say P takes 1 to I, and P takes I to J, let's say, something like that. In general, let's just say P takes the number J to the number K, okay? So I define for this, let's say this is P1, P2, P3. In general, I assign the matrix for the permutation P. If P acts on J, if P maps J to K, then I put a 1 in the matrix DP for the JK element. I put a 1. So this sort of defines it. I just look at the matrix elements. This will become clearer when I do an example in a second. If this maps into this object maps into this under the permutation, then I put a 1 in the matrix. So let's do this for S3. So for the identity element is always represented by the identity matrix. And it just maps, you know, you can see, again, the first basis element. What we're doing here is we're using these objects 1 to n. It's sort of like we're using them as our states, as our vectors that the matrices are operating on. So you could think of this as so 1 goes to 1, 2 goes to 2, and 3 goes to 3. Now if we do the next one, so this is D3E. Let's do D3. I'll do, I erased all the things, but let's do R1, and R1 is equal to 2, 3. So what this does is the first object doesn't map anywhere, but the second object maps to the third, and the third maps into the second. So this is just going to be 1, 1 maps to 1, 2 maps to 3, and 3 maps to 2. And what you'll find is in the defining representation for the permutation group, there'll be a 1 in every row and a single 1 in every column. And it's just like you permute them. So D3R2, this is represented by 1, 3. This just goes to 0, 0, 1, 0, 1, 0. 3 goes to 1, 1, 0, 0. And D3R3, this is 1, 2. Okay, and then for the rotations, again, 1 goes to 2, 2 goes to 3, and 3 goes to 1. This is 1, 2, 3, and this is 3, 2, 1. So 3 goes to 2, 2 goes to 1, and 1 goes to 3. Now, if you look at these permutations, there's something very interesting that you can notice, which will come up in a while. First of all, if something is an n-dimensional representation, the trace of the identity element is always n. So the trace of this is 3. The interesting thing is for the reflections, the traces are all the same. It's 1, 1, 1, 1. And we'll show that because they're in the same class, they have the same trace. And here the traces are all 0. They're in the same class, they have the same traces. Now, the interesting thing about this representation, it looks very simple and everything, but this is not an irreducible representation. This can actually be reduced. And I'm going to show you that reduction right now. Okay. So I left some things that I didn't, terminology I didn't get. 2 representations. If D prime for all G is equal to S inverse DGS, these are what's called equivalent representations. Same thing as like similar matrices. And you can see that if this is a representation, then this will automatically be a representation. Because when you do the D prime G1, G2, you're going to have a G1 here, and then you're going to have another thing, and the S inverse cancel, and the D G1, G2 becomes D G1, G2, and then you have the same thing. So you'll see that if this is a representation, then this is a representation. Furthermore, for finite representations, finite groups, all reps are equivalent to a unitary representation. This is very important because basically from now on I'm always going to assume that D dagger G DG equals DG D dagger G equals the identity. So we can always work, there are representations which aren't unitary, but they're equivalent to unitary reps. So we're always going to assume we're working with the unitary representation. And another thing for our theorems is we're going to always assume whenever we have a representation when I talk about the number of representations, or this reduces to this plus this, I'm taking the canonical representative of the representations. I'm considering all representations that are equivalent to each other as being the same. So keep that in mind. Now, I want to show, I just want to illustrate that this representation that I gave, the defining representation for the permutation group, is reducible. Okay, there's two ways to do this. One is the hard way. Literally, if I define S as 1, 1, 1, 0, 2, square root of 3, minus 1, minus the square root of 3, and minus 1. Using that formula, S inverse each of these matrices S, you can get the reduction. So this is something you can work out if you want on a computer using a computer algebra system. It's a lot of work, but this actually reduces this representation. And I just want to show what the reduction is. And the reduction is as follows. I'm going to call it D3 prime, even though this is, nothing's ever going to happen to the identity. Okay, I'll do the other three in a second, but if you actually were to apply this S to these rotations, you would get this. And you notice these are in block diagonal form. There's a 2 by 2 block and a 1 by 1 block, and these are zeros. And interestingly, the 2 by 2, remember I said where did this come from? If you actually perform this reduction, you get, well, maybe I got that written wrong. Well, anyway, I might have mixed up these two matrices here on the signs because I'm using two different books and they're using a different convention. But you can see that this is block diagonal and it's one of these 2 by 2 matrices. This one corresponds to that and this one corresponds to that. And if I were to do the, I'll just do one example. D3 prime, let's say R2, one 0 0 0 1/2 minus the square root of 3 over 2, 0 minus the square root of 3 over 2 minus 1/2. And this also corresponds, if we look at the, see if I got the sign right, but again, here, this 2 by 2 block corresponds to this two-dimensional representation. And in the, we always have a 1 in this block. And let me just do one last one. So this one is diagonal. But again, the fact that we can make one completely diagonal, if you see this 2 by 2 block, corresponds to that. And then the one over here. So what is true is that for the defining representation of S3, and part of what we'll do in the next few lectures is to show where we get these things from. I'm just sort of writing down the answers now. But what we've essentially shown is D3, the defining representation, is equal to D. Anyway, it's D even, D1, or even the direct sum of that plus D2. And what's interesting is that the 1 prime does not occur. So this is an example of a 3-dimensional representation. This is the reduction we want to do. We want to get its component parts and do that. And we'll see the use of this later. I want to cover a few more things right now real quickly. For any group, there is the regular representation. Don't confuse regular with defining. The regular representation is very simple. It simply takes all the group elements and uses them as basis elements. So let's say the group is, let's say there's n elements. The vector space for our vectors is going to be G1, G2, dot, 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 G, I'm sorry, Gn. Now it looks like that defining rep, but remember for S3, n equal 3 factorial equals 6. So here we're not defining the objects as the basis elements. We're actually defining each permutation as a basis element. And I define the matrix D, I'll put R for regular, and let's say for the group element G1, acting on the vector G2, we're just going to define this as G1, G2. This will hold for any group, and you can check that it's a representation. And so it's kind of like easy for S3. Let's say I wanted to know what dr, by the way, it's easy to show. This has the same property like in the defining representation. There's going to be a 1, except for the identity, there's going to be a 1 in every column and a 1 in every row, and that's it. But let's do like dr 1, 2. Okay? So what we can do is we can make this big matrix, label it by like E, 1, 2, 1, 3, 2, 3, 1, 2, 3, 3, 2, 1. E, 1, 2, 1, 3, 2, 3, 3, 2, 1. Okay. So if I want to know what the action, basically if I want to know what 1, 2 does to the identity element, it just multiplies it by 1, but it just makes it 1, 2, like dr 1, 2 acting on this is just equal to 1, 2 times e, or it's just equal to 1, 2. So that means that the identity is mapped to 1, 2. So there's a 1 here. Okay? And if we take the 1, 2 element, where does that get mapped on? 1, 2 goes to E. So that would be 1 here. And then where does 1, 3 go to? And then everything here, this is all going to be zeros. And then what is 1, 2 times 1, 3? And using that trick is 2, 1, 1, 3, which is equal to 2, 3. I'm sorry, 2, 1, 3. So that's 1, 3, 2, which is 2, 1, 3, which is here. So 1, 3 is, there's going to be a 1 here. And I can do that, and do that, and so on. I can fill out the rest of the table. So this is called the regular representation. You might think, why do we need this representation? Well, it turns out the regular representation for any finite group is reducible. And not only is it reducible, but it's reducible in a very special way where the number of times the representations appear will all appear on the diagonal. So we might have something like this, a one-dimensional representation, a one-dimensional representation, a one-prime dimensional representation, a one-prime dimensional representation, and a two-dimensional representation, and a two-dimensional representation. If this is the way the regular representation reduced, and in this case that's not right, it's actually, I believe, it's like this. D1, D1 prime, D2, D2. There's some theorems we'll prove, but all the irreducible representations lie along the diagonal, and the number of times they occur ends up being, so this is like one whole representation here. I wrote this wrong. You can see the regular representation is always going to be if there's n elements in the group, it's always going to be n by n. So for like S3, it's going to be a 6 by 6 matrix. And we can put it in this form where there's a one-dimensional representation here, one-dimensional representation here, then a two-dimensional representation here, and the same two-dimensional representation here. So we get all the irreducible representations on the diagonal, and the number of times a representation appears is equal to its dimension. So this appears twice, each of these appear once. We'll, I'm not sure we'll prove this, but this fact will be very, very useful. So that's the regular representation. And I'll come back next time and I'll start talking about direct product representations and tensor products. And we'll do that triangle symmetry a little bit more carefully and start showing how the physics of it works. So I'll see you next time. Thank you.